Okay, you guys should be able to hear me now. Yep, that's my mic right there. So I had it hooked up to the other computer. I've got two computers running right now. So can you guys hear me now? Good, awesome. I'll have to cut out this whole start of the video, but right, to make sure there's no sauce for my sandwich and all that good stuff. But mic's working, everything's good. Hey, Will, how you doing? I can't see how many people are watching because my computer is blocking that. Oh, I'm getting a feedback. Oh, because I'm watching my own video. So, everyone ready to start reviewing here in a second? They actually just changed YouTube Studio, and this whole last 30, 40 minutes, I was getting everything set up, but there's now a new YouTube Studio, and the update had me trying to figure out where all the buttons are that I need to press. So, we'll start showing some stuff here in a second, but let's get started with the review. I need you guys to interpret the output, and let me see how many people are watching. Let's go over here, and let's hop onto the channel and just see how many people are watching the review. I don't know. How are you doing today, Will? We'll go here to... There's a little bit of a delay. Awesome, Will. Glad to hear you're doing great. Oh, I forgot. I put a keyboard. I have two keyboards to type to you guys. And so I can do one person watching. Oh, my. I thought we'd get more people than... Oh, 7 watching. Good, 7. Okay. And cool. So you guys can see the face in the screen right here. And we're doing well. So let's hop in and start doing some discussion here. So... got a whole bunch of stuff open. Let's open a new tab and actually let's start learning. So here, let's go over here to a new R script. And what is everyone confused on? We got 7 people watching right now. What is everyone confused on, or does everyone have questions on? What is everyone confused on or has questions on? So here, let's go ahead and clean the global environment. And go right here, clean the global environment up. Anyone have any questions? We'll start the review and start talking about stuff. And once we've cleaned the global environment, I guess a few things I've noticed is when you run reg class, well, one, you need to run it when you start R because you don't actually have anything loaded up when you start R. So if you want to look for functions like all correlations, you must have reg class on, hence why it says reg class there. Or if you want to look for something like associate function, that needs to have reg class on. So we can look at some of the outputs there. And a lot of people I see for their take home, which is due Sunday night, are doing things like data, data 2, or load, data 2. I see a lot of people doing this. These don't do anything, at least with what we have right here, that's not going to do anything. So what we do once we make the midterm, which I don't have the make midterm function in, if you had the make midterm function in here and you put in your number, don't put in that number. If you had the make midterm function in, it'll make your midterm and the data will be loaded in the global environment. You should see it over here. I've had a few people email me saying, Brian, my data went away. What do I do? And if your data goes away, just remake your midterm, use the same number. That's why you want to keep everything stored that you're doing. If you remake your midterm, it'll make it with the same data. So that's all the good stuff right there. Surely there are some questions. What output do you guys want to look at? What output should we look at today? We could start at the very beginning, but I need some user-driven questions here. So what output do you want to look at? Because basically the output is pretty much what the test is. I'll turn the mic a little bit more towards me. So the output is pretty much what the test is. So let's see. Will, I'm giving you 1,000 points. You're the only person talking to me right now. So there's always a little bit of delay, so I have to pause after I say anything. So feel free to tell me any output you want to see, and we can start just making output, analyzing output. And that's kind of our goal, is if we know what the output's showing us, then we understand how to read the data and what's going on. Because let's go in here and let's see. I'll load up some data. Survey, we don't really load up data survey 11 much. Can you briefly go over to ways to detect normality and linearity in charts? Cool, yeah, let's do that. So Okay, can you help with the bonus number 9? Tell me, is that the extrapolation check? Or no, that's, tell me what that problem is, Will, and then I'll talk about that here in a moment. So if you notice, I just loaded in the data survey 11. This is how we load in data if it's in a package. So that's how we do this right here. Now I need to, I've got like 3 places to look right now. Okay, make a linear model. And this is not a required function right here, but I'm going to take a look at just the structure of survey 11. That's the structure function right there. And that is helping me just examine what's going on with the variables. So we could take something like, we want to do a quantitative analysis here. Let's go to hours of sleep per night. This is how much sleep people get a night. I'm going to copy that. I'm going to put that right here. Or I thought I did. I guess I didn't copy it. So hours of sleep per night. Let's try copying this again. There we go. And let's try putting it there. Oh, it doesn't like that sort of copy with this keyboard. Oh, I'm using a PC keyboard on a Mac. And so that is, it doesn't like the buttons. So that is why. And let's continue down to fastest speed in a car. So this isn't going to really give us one of the best relationships right here, but I hope the people are not, you know, faster they drive in the car, the less they sleep. We'll see what the relationship is here. We need to do data equals survey 11, because that's where this is located. All these variables are inside of this data frame, so we have to make sure to tell it to go to this data frame to analyze this. And yeah, we'll talk about a partial F test. Yeah, I can do that one on here in a moment. That won't be on the test, but it is a bonus, so we can do that. So we've just created a linear model. We'll do the linear in a second, but really one of the first steps, see, and then we'll do kitties next here. When we analyze this right here, what we're looking at is the output from the regression. And let's look at the output. So we've got the intercept, and we've got the X variable in the model. And you should be able to talk about all of these things and understand what they mean, and it doesn't hurt to have the visualization of the model right over here. And we do see a model that is really nothing. This model is kind of useless. And let's go through all of the output real quick, and then we'll see if linearity holds, which actually, looking at this, I might be able to zoom in and make it look a little bit better. It doesn't look like linearity is a problem. A lot of times if you make the plot a little bigger, it won't give you the issue with the loc stuff, or the location of the legend. So that helps out a little bit. Or you can cheat and make that go away and do something like that, and that takes off the screen. So overall, this looks like a good regression, but one that is not statistically significant. And if you look at this, I love this. So answer these questions if you're watching now. I'll probably try to answer them, because even at a low latency, we're at like 5-6 seconds, then everyone has to type their answers, but type it in the chat so I can see it. When you look at this model, it should look a lot like the naive model. And the naive model is the mean of y. If you notice here, it's a flat line, and you could actually create the naive model for this very easily. Just remove this, and you will see. And I don't think it'll plot it for us. It's not plotting it for us, but if you notice here, the intercept for the naive model with nothing in it is just the intercept, and that's actually very, very similar. That 6.8 such and such is very similar to the 6.9, and this is our model where we actually have data. So this is basically just the intercept. So there's really not anything going on right here, and I know that more so because of the p-value. These are things that catch my eyes when I look at a model right away. I'm like, okay, this x variable is not statistically significant in predicting y, as in it does not increase the sums of squares reduction, or it does not reduce the sums of squares in a significant way. And as we were talking about in multiple regression, that's what we're looking at here with this same p-value. Now that's for the whole model. So we have two things. We have a p-value for an x variable and a p-value for the whole model, but in simple linear, which is what our test is over, the x variable is the whole model. So this one x variable is the whole model. So does that x variable, when it's included, reduce the sums of squares in a significant way? Well, it's not competing with anything right now. I'll try not to talk about multiple too much, but it's not statistically significant. And also the r-squared is completely horrible. Only about 0.016% of the variation, because you times that by 100, is explained in hours of sleep per night by the fastest speed someone has driven a car. We see right here, if we were to use fastest speed of driving a car to predict how many hours a night someone sleeps, we generally miss by 1.1 hours. Here's a big note on residual standard error. It's also RMSE, root mean square error. It's how much we usually miss by, typical miss when we predict, and it's in units of the y. So when we predict how many hours a night someone sleeps, we typically miss by about 1.1 hours. Make sure that's in units of y. And you can really see it over here. If you notice, what is a 95% confidence interval for pretty much everybody? Just give me a 95% confidence interval for pretty much everybody. I want to see in the chat. Like, if you had to give me a 95% confidence interval for pretty much everyone, you'd be like, I'm 95% confident pretty much everyone sleeps between what and what? On average. Like, the average hours of nights people get, average hours of nightly sleep people get is pretty much always between what? I'm 95% confident that it's between, and I'll wait a second more in the chat. And you can see it in the graphic, or you can solve it mathematically. So the answer would be 5 to 9. 5 to 9. 6 to 8 would be a 68% confidence roll. And you see how that's one standard error right there? So if it's a 95% confident, it's 2 standard errors. And if you look right here, estimate for... Yes, because if you look right here, here's our estimate for the y, and then there's basically 2 standard errors right there. And the residual standard error and the standard error of an individual are very similar. They're not the exact same thing, but you can see graphically right here that pretty much all people sleep between 9 and 5. That's what that's showing you there with that graphic. We're kind of melding all the graphics and all the information with what they mean here, because that's just a confidence interval for all individuals. If you notice, it only misses just a few people. So we're pretty much confident that all people get on average about 5 to 9 hours of sleep. So that's, about what we see right there. And let's look here what else we have. Do not worry about the degrees of freedom. Nothing on the test will be related to degrees of freedom. You basically in this class never need to mention the degrees of freedom. So now let's talk about this estimate, and try this in the chat right now, or try this if you're watching the video at home. Write the regression equation. I know it's going to be a bit messy, but try writing the regression equation right now and do it with the context of the problem. So try that in chat and give it a shot. I like to do it where you guys answer the questions, because you need practice. You have to, it's one thing to hear something, but then you have to actually try writing it down. So if you have a sheet of paper right now, write down the regression equation. So use the estimates to write the regression equation, especially if you know the y we're predicting and the x we're using. This should be pretty quick. After you've done it 4 or 5 times, you're like, oh, that's free points on the test. And I want there to be a lot of questions where you think it's free points. And write the regression equation should be one of those ones. It's very standard, it's very methodical, and you do get your cheat sheet. So if you take output like this and then write the regression equation, you should be able to do it. So I'll see if I see it in the chat. I'm throwing 200 points for any answers in the chat that people give. So earn some extra credit. I think Will has it right here. Will, you got it correct, Will. Now, it is very mathematically correct. I would just switch B0 and B1. You have classic y equals mx plus b. If my graders took off points, I'd give them back to you because it's mathematically equal. And I like that you did it in context of the problem. Will wrote, sleep per night equals negative 0.00079 times fastest car speed plus 6.9582. And 6.9582 is the intercept, it's B0, and then B1 is the coefficient of the slope, and I like that Will took off the x22 because that's just coding for the variable. Now, what you'll notice here, let's do this one real quick. Just round the numbers, and let's talk about how to make 95% confidence intervals. And if you can't tell, I'm kind of leaning towards how I write my test questions with this review, with the questions I'm asking you that you should be able to do. So if you're like, wait, let's talk about this, which we will do the test here in a second, I promise. Realize everything I'm talking right now is very fair game for the test. So when you see on the test, like, make a 95% confidence interval for the intercept. And I'm asking the intercept just because it's a little bit nicer numbers right here. You can go ahead and round it, and then I'll show mathematically how to do it on here. Plus, people watching the video can see the chat if they're watching the recording of the video. So go ahead and try to make a 95% confidence interval. And try doing this on a sheet of paper, and I'll do it pretty much exactly right here. Oh, I cannot copy. Darn Mac and PC keyboard. So I am making a 95% confidence interval for the intercept here, and it's pretty easy to do. Let's think about what I am doing and why, and what theoretically is 95% confidence interval. Now, okay, I'm throwing this to Sophia here for another 200 points. What am I building here? A 95% confidence interval or a different type of confidence interval if I do this with plus or minus on this? So this right here would not be a 95% confidence interval yet. It would not be a 95% confidence interval. What kind of confidence interval is this right now with the numbers I'm using? What kind of confidence interval is this? Hint, let me put in a little more stuff right here. Well, I think if I do it, let's find out the hard way. Let's put times 1 right here. I think that will do mathematical operations correctly. And no one's saying anything in the chat yet. And let's run this line of code. And there is basically not a 95% confidence interval, but a 68% confidence interval. We can make it a 95% confidence interval by going out 2 standard errors. So I'm going out 2 standard errors now, and I have a 95% confidence interval. And we can confirm this by taking our model and actually making 95% confidence intervals. Oh, and I just have the intercept right now. Let me reload the model with the stuff in it. Sorry, I only have my intercept model right now. That's the current model stored. Let's confirm our answer and see how we did by going plus or minus 2 standard errors. Now remember, 2 is not the exact amount we go plus or minus. We let the computer usually do that for us. So the computer will go the exact amount for us. So we're just rebuilding our model right here because I had written over it. And there's our model. And we're just going to go plus or minus 2 standard errors. That's what I get mathematically. And there it is right there. So if you notice, going 2 standard errors, I get this right here. Many people I always say in class, what's the exact number? And everyone says 1.96. Whoops, 1.96. 1.96, and that's for z-scores. But z's are basically t's. Basically. They're more exact, and if you notice now, using the z-score, I get very close, but the t-score is maybe 1.97 or something like that. So a lot of times in our heads, we just go 2 standard errors. We just go 2 standard errors right here. So does everyone see what's going on mathematically, how you would do this on a test? If you wanted to make a 95% confidence interval, you have your estimate. You have your estimate right here, and you have your standard error, and a 95% confidence interval is plus or minus 2 standard errors, which you're basically, and I like this right here, because you're basically seeing that right here. Here's 7, that's basically 7, and then we have the residual standard error right here is for like an individual. So when we make predictions, we're pretty much 95% confident that whatever we predict will be in this range. That's not exactly how we make that interval, but it's kind of close, at least for this example, and a little bit analogous. This is a confidence interval for the intercept, telling us where we think this red line is hitting right there. But let's check some conditions. And looking at this right now with checking the conditions, this is probably going to pass. I think it's going to pass all of them. Okay. It does not pass normality. It looked pretty good just visually speaking. Here's where we check the conditions. So checking the conditions is done with check regression. And let's go through our steps. Step 1 is to look at the p-values. If the p-values are below 0.05, there is an issue. So make sure you've written down step 1 is to look at the p-values. So the only issue here I see is what? The only issue here I see is an issue with what? Where is there an issue with this one? There is an issue somewhere on this, and where is it? In the chat. I think this was Sophia's question. Yes, this is Sophia's question from earlier on. So you should be able to quickly identify the only issue with this plot is it's what? This would be a very good and quick test question. So this one right here, since this is the issue right here, that the p-value for normality is 0, so that tells us there's an issue with the normality of the residuals. So the normality of the residuals all the way over here, this is the normality of the residuals, has an issue. So the linearity, which is the linearity of the x of the overall model, these two tests in a simple linear come out the same. So there's really only 3 tests. We don't need to test each x because our x is the model, but the linearity is okay, and the equal spread is okay also. The equal spread is actually one of the best ones. So when we look at these tests, the p-value being low, and if you think classically, I think this helps people. Classically speaking, the null is we are good. Like there is linearity, there is equal spread, there is normality. That's the null right here. So if you have a low p-value, you are rejecting that there is normality because the null was there is normality of the residuals. The alternative would be there is not normality of the residuals. So make sure to kind of understand right there the distinction. that when we are doing this test to check the assumptions, we are checking the normality. Now, I do want to point something out. Let me make a different model here, one that's a lot easier to make. So let me load up data survey 10. It's got shorter names to it, and I know the names of those variables a little bit easier. We're going to make model 2 here and kind of look at this. And a lot of this test is over simple linear. I would say about 40, 45, 50% of the test is over simple linear. It's a major, major component, but we did have the building blocks to get up to it. If you see here, we do height, and we do weight, and we do data equals survey 10. These are variables inside of survey 10. And let's take a look right here. With this right here, let's load the summary. Is somebody's weight significant in predicting their height? So we're seeing if weight is significant in predicting their height, and the answer is most definitely yes. The p-value right here. And at this point, you should instantaneously be able to write out the model. So if you see this, you should write the model out very quickly. We should also probably visualize our model just to see it. Just a very common step to get the visual. And I'm going to remove the location, make it a little further away so we can actually see if there's any points there. And I'm going to do one other thing. I'm going to take this line of code right here and copy it. And I'm going to plot this. One weird thing is that the visualized model that Dr. Petrie created doesn't always get every point. And it looks like it did a pretty decent job here. You see this outlier here. And just the way it orients it sometimes, it tries to make a certain orientation. So you can get every point there. And you see it kind of flattens out. So this is our model, and this is our model. We could always go right here and add in abline m, comma, red, col equals red. And we can make our own plot. Oh, it's AB line 2. Sorry, I was like, where'd it go? There we go. We can add in that line right there. Now, just looking at this visually, what do you think will be one of the conditions we fail? Looking at that visually, what do you think is one of the conditions we will fail? And then this will lead into, I believe, we can do this with Kitty's question right here. So looking at this visually, you should definitely see at least one of the conditions it'll fail. And look right around here. Because look at the line, and then look at this. What we're seeing right there is issues with the linearity because the points are below it. So that doesn't mean we fail. We actually need to look at the check regression. Now these p-values in check regression are for the conditions in the model. And actually, is my model good or does it have problems according to the p-values? Is my model good or does it have problems according to the p-values? You guys can do like one-word answers if you want. If you're like good, bad, or is my model good or does it have problems? So whatever you think. And make sure to be answering these questions at home. Pause the video and be like, you just have to be able to read the output. If you can answer it before I can, you're getting it right and you understand. Remember, the test questions just come from me looking at the output and saying, well, what can we learn from this? Sometimes you might have to write out what I say or choose a multiple question or write an equation or something like that. But it's mainly just analyzing the output and knowing what it all means and how it relates to why we're doing the statistical technique. So all of these p-values here are actually very bad. They are below 0.05, meaning we reject the null for all of them. The null was linearity. We reject linearity. Exactly, Will, you're right, bad model. So equal spread is also bad, and normality of the residuals is bad. The p-values right here for linearity are seen right here. And if you notice this bend at the end of the model, if you saw previously, this bend right here, these points that are all below the line, you see the same pattern right here with these points all below the line. You also see these points way down below, and we go back and we see these points way down below. So that's what's going on right there. We see a bend in the model, some sort of curvature at the end. Now we go over, well, we look one more time here, the equal spread. Yeah, there's maybe an equal spread issue. There's also outlier issue. There's outliers here. There's outlier here maybe, and then there's a little bit of like something weird going on with the spread. There's definitely some sort of non-linearity to it. And then we look over at the last plot, and the last plot is where we look at normality. Now, a lot of people look at this last plot and think it's linearity. It's just, we're trained, we see a line, we think linearity. But this is saying the values of the residuals if normal, and that's what this is. And then these black dots are the observed values we have. So it's kind of plotting what we expect via normal and what we observe via normal. And this is what we should observe if it's normal. And our model definitely trails off right here. It has way too many low residuals. If you see these points across here at the bottom, these are these points here, and these are these points here. So this is not the worst model in the world, but it is kind of bad. I'm not that happy with this model. But let's review the 3 steps to see if we should use a model. Step number 1 is look at the p-values. And if the p-values fail, you go to step 2. Step 2 is to see if your sample size is more than 25. And you see that down below right here. Now, this is not a condition. There's no condition sample size more than 25. We're just seeing if we can investigate the diagnostic plots. If our sample size is less than 25, we stop. As it says, sample size less than 25, you have to pass all these tests. If it's greater than or equal to 25, you can look at the diagnostic plots to see if the violation is severe or if it's small enough to be ignored. And actually, a good theory question is, why do we look at the plots? Like if we have a sample size of 10,000, why would we look at the plots? So why, I mean, we failed the tests. That's bad. We know that the conditions are wrong. It's very interesting what the answer is. They might be typing in the chat. But the truth is that all models are wrong. And we keep saying that. All models are wrong. So we know that our model probably has a bunch of issues. Our model that we made, this line, does not perfectly describe reality. So even if we have amazing models, if we get enough data, exactly, Kitty, you are correct. With enough data, it basically finds out our model's wrong. Really sensitive if n is high. So, and that's exactly what it says in the notes. So basically it goes to, it's going to figure out our model's wrong with enough data, and it's going to tell us there's an issue. So that's the issue right here, is that if we have too much data, this test becomes too sensitive, and it will tell us we have the wrong model. And it's right. I mean, we have the wrong model, but it's like, is our model, and this is a good phrase to remember, a reasonable reflection of reality? And at this point, I would say this model is not a reasonable reflection of reality. And what we could do is we could try to do a transformation. And so this goes into Kitty's question here, and then we'll start doing a partial F test in a moment. So we can go to find transformation, and we can run this function right here. And I don't know if this fixed it. Too many transformations. It says we should raise it to those powers. We can see the residuals here. Ooh, look at that. Look at that. Wow, look at that faraway point. That point right there is causing the problems. It's probably this outlier here that's being transformed and is now over here. This does increase the R squared from a value of 0.361 to 41%. That's pretty good. I mean, it's I don't know, like a 1/7 or, yeah, it's like just thinking mathematically, about a 15-16% increase in R squared, which is good. But overall, I think it's about an 11% increase in R squared, or 11 to 15%. But I don't know. There's still this ridiculous outlier over here that's causing problems. And if you look at it, this is actually data validation, which we talked about earlier on. That person entered in 75 for their height and 75 for their weight. So they're as tall as I am. They're 6'3", and they weigh 75 pounds. And that's not quite true. I'm over here in the bulk of the data here, and they're 115 pounds lighter than I am. I think they misentered their data. So we could remove them and remake the model. It would probably help. And actually, let's see that. It's very easy to remove someone. All we have to do is find them. We go to min of survey 10, and we want to do weight. And that's the min weight. So now we found them. And we can do which.min. And that tells us they are in row 544. So now we remake our model, but we remove row 544. This will actually be in your next assignment. And Kitty, I'll do that in 1 second. Then let's see. Oh, they're gone. And let's see if now we get it better. And let's see what, I think Kitty had an additional question. So now it does a little bit better. What if none of the transform models have an R squared value greater than the R squared of the sample linear? Did it say that when you returned it? When you ran it, did it say like there's no better transformation? And if it does report values really close, if these values are super duper 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 close, then it's just decimal differences that you can't see. There are decimals behind the scene right here that are like 0.4353, 0.4352. So the way especially the checker works, when I run the checker, if you get any models, you said, is it possible and are better than the simple linear to answer the question, would we use the best of the top 3 transform models or which which question are you talking about the choose order one on the take home? Which one are you talking about, Kitty? If you can, copy paste your question in the chat so I can see it. And I don't have your data, but I can take a look. And I think we can do Will's question here too. I think Will had one. So Will had a question too, and let's talk about Will's question right here. But copy paste that question. I want to make sure I get you all the information you need. So we can remove that outlier right here because they are data that was not really, someone's probably not 75 inches tall and 75 pounds. I removed them because they probably don't exist. I don't think they entered their data incorrectly. So we removed them. Let's go ahead and take this model right here. So conduct a partial F test. Yes, let's do that. Now, here's a big thing, and I'm just going to drop some major hints. I need you guys to say this in the chat. If I'm going to look at the significance, okay, yeah, thank you, Kitty. We got time. So we will. I will look at it then. So let's do this. Let's make a model, and I want people to do well on the take home. I want you guys to tell me how I can, and this is a common mistake, I see it all the time, so if you're watching this video, you probably did better on the take home. Sure, I'll enter this in. This is take home related now, and we will try to also talk about how this relates to our test. So here's a model right here. Don't worry about that do try. It's just a graphical error. It happens all the time for some reason in R. I don't know why. I think it's because it's seeing my figure over there. But I have here a multiple regression model. Now, how can I look at the significance of the variables in my model? How can I look at the significance of the variables in my model? I need you guys to tell me in the chat, how can I look at the significance of the variables in my model? What can I run? It's on the screen somewhere. Every time you have a code, always be like, what does this code do? Could I tell someone in words what this code does? And how can I look at the significance? You are very correct, Will. You are correct on summary. You're getting tons of points. Every question you guys ask or every question you attempt to answer, you get points. Just keep answering in the discussion. It definitely keeps us flowing. I like it. So what are my two least significant predictors here? What are my two least significant predictors here? This is a huge help. I'm going to copy paste this model while you guys are figuring that out because I'm going to be making some changes to it. I'm going to be calling this model 4. What are my two least significant predictors? So you guys might know. I'm already ready to go on it. What are my two least significant predictors? You are right, GPA and text per days. These are the two least significant predictors in the model. Overall, the model is significant. So the model itself is significant right here. We can see that. But the predictors, GPA and text per day, are not significant. Now, I want to do this real quick before I make this next model. I want to do a check regression on this model. Now, what is, and interestingly enough, oh, that's so... This is so interesting. If someone did it this wrong way, they would have lucked out and actually gotten it correct, but not on purpose. What do these p-values here represent? These p-values are p-values for what? As in when it says linearity, and it has an x here, linearity and x, equal spread, normality, these are p-values for what? I see a lot of people doing this because they just did something like this, so they're like, aha, I got p-values. But what are these p-values for? What are they doing? You might be saying in the chat, they are checking conditions. This is not the significance of something in your model. This is checking the condition for the linearity of that x in your model. So this is not, these p-values you're looking at right now from check regression are not the significance of an x in the model. To look at the significance of an x in the model, you have to run summary. Summary is the significance of your x's in the model, where check regression checks the conditions for your model to see if things like linearity for each x are met. So here we go, Will. And you've been answering so much, so I'm more than happy to pretty much give this one away. Now remember, I'm removing these not because of the check regression. Actually, these are the best when it comes to linearity. Desired weight and weight have issues with linearity, where in the reverse right here, GPA and text per day do not have a statistically significant relationship. Excuse me. We're not talking simple anymore. GPA and text per day do not significantly reduce the sums of squares when we add them to the model. So that's what we have going on right there. And so I've made my second model right here. If you notice, this is model 4. And we can just, let's delete this out. Oh, no, it doesn't. That's the Stat201 project. So, and let's go right here and go ANOVA. And the way to read this ANOVA for the partial F test is, do I have evidence to go from my simple to my complex? And if you notice, I didn't write simple there. I didn't write complex. A simple model, ooh, I reversed it. Simple is number 4, and there we go. A simple model is a model that has less variables inside of it, where a complex model has more variables. So you notice the simple model, model 4, only has 2 variables inside of it, where the complex model, model 3, has 4 variables. And you can see that right here in the output. Your simple model is the first model you enter, and the complex model is the second model you enter. But models just have names. I mean, when I teach it, I usually write simple and complex, but the idea is, do I have evidence to go from the simple to the complex? And if you're looking for the p-value for this, it is right here, and that tells us if we have evidence to go from the simple to the complex, and do we have evidence to go from the simple to the complex? Do we have evidence to do that? Do we have evidence to go from the simple to the complex? The answer would be most definitely. It's like a 50-50 shot, and I feel half the time people get it wrong, which always scares me. No, Will, you are exactly right. No, because the p-value is greater than 0.05. Exactly. Because it's, do we have evidence to go from the simple to the complex? And if you look at the reduction in sums of squares right here, it's very small, and we get a small f. So the f is that we saw a reduction that was only about 64% of what we thought would be by random chance, and it's not a significant reduction. So we would keep our model here with just height, explained by weight and desired weight. We would not include the 2 other variables because they do not significantly reduce the sums of squared error. So I think, Will, does that help you out a lot with that question on the take-home? I think that should be pretty much self-explanatory on how to do it. I think I'm trying to see if there's any other questions in here. I'm probably going to start doing some of the associate function right here and show how to read associate output. So I think it will, if you have an additional question, feel free to ask. Thank you for all the questions. I think that should maybe make sense with the take-home now. Let me do association between weight and gender. We'll do some of the obvious ones. Sometimes I try making them more business-related for the test. Remember, the test only goes up to simple linear regression. Now, when you see something like this, I oftentimes want to ask questions like, and I might ask questions this year, like, what kind of output would this create? Because you kind of need to know what you're going to do and where it's going to go. And we're predicting y, which is weight, which is quantitative, and gender is categorical. So we should get box plots here. So when we run this, we get box plots. I'll increase the output size so we can see it a little bit better. But we get the box plots showing us the weights for males and females, and this should help out with the output size. Did that do it? Okay, good, did it. Ooh, and I do see something interesting here. This will be a good bit of a review because we haven't talked about this in a while. Now, I actually like looking at the output here first because we can see males weigh more than females. But here's a very important quick question on the test, and you'll even see it as one of the first questions on the test I gave in spring 2017, which I have posted. I have one of the tests with the keys posted. Looking at this output, I want you to tell me, should we use means or medians to analyze the data? Means or medians to analyze the data. And basically, I like to ask people, and I've done it on the test, circle the graphics that tell you this. Circle the best graphics to tell you this. Now, there's 2 graphics to look at. I do kind of like it because people often choose a wrong graphic, which I understand why they choose it. But there should be a graphic you look at to tell if we use means or medians. And let's break down how we're deciding it. To use means or medians is based on, is the data normal? So if the data is normal, we will use means. If it's not normal, we will use medians. To look at if the data is normal, we should look at the QQ plot for normality. And if you notice, it's values of weight if normal. This is once again checking to see if it's normal, like we just checked the residuals. So you should know this is called a QQ plot here, or a quantile plot, normal probability plot. It goes by many names. And so this red line here is the normal. You see the major departure due to the high outliers. And so we have good evidence that this is not normal. And especially the female distribution right here, I would say is pretty strongly skewed. You can see it up here in the box plot, but this is really the one you want to look at. Box plots are probably the worst way. Histograms are the second worst because we decide the bin widths. Box plots don't really show you a good shape. and this plot right here shows you what it should look like if normal, and we do see a departure from normal that is, in my opinion, too big. I think that's a little bit too much of a departure for me to feel safe using means. So we go back to the output and we use medians. Is this difference statistically significant? So is this difference here statistically significant? Is this difference statistically significant? Where would we look at for that? Circle the p-value that shows you that this difference is statistically significant. Just think about that. Pretend, like, pause your video and see if you circle the right p-value, or circle the value, give it a little bit away there. Circle the value that tells you that this is statistically significant. I like, while I'm doing this, to kind of think of test questions. I think that would be great with this output. Like, circle the output that tells you this is statistically significant. And the one to circle would be right here. We'll keep making this like an interactive video if you're watching it at home, so you can pause it and try to answer the questions. How about, how are you certain that the output is statistically significant? Well, that requires a confidence interval right here. The confidence interval right here is how you are certain that it is statistically significant. So right here we have a confidence interval telling us I am 95% confident that the p-value is contained in the interval 0 to 0.007. And this is for a p-value, and we do not want intervals for p-values to contain what value? Intervals for p-values should not contain 0.05. 0.05 is the point at which we say things are statistically significant. So if it contained 0.05, we'd be like, I am uncertain. Exactly, Kitty, you are right. You'd say, I don't know if this is statistically significant. It could not be, or it could be statistically significant. And what is there a practical significance to the measurements you've made right here? Is there a practical significance? Are the differences here practically significant? And what value do you assign to the practical significance? This one always trips people up. But if you're thinking about practical significance, I want you to think about this. Practical significance should make sense to someone who does not know statistics. So if it's practically significant, someone who does not know statistics should be able to understand it, and you should be able to explain to them why it's practically significant. So you don't want to say the probability of our results or results from our stream happening by random chance are basically 0. That's a good interpretation of a p-value, but that's also statistical significance. So when we look at practical significance, we're analyzing the medians. So right here, the difference between the medians of males and females for their weights is 45 pounds, where males weigh 45 more pounds than females when we look at the 50th percentile. Also, I mentioned 50th percentile instead of saying median. I don't know which one's better for the general public, but I think most people understand that if you took the basically average male at the 50th percentile, compared them to the average female at the 50th percentile, you would see a difference of 45 pounds. So that is the difference practically significant? And we can switch up the question right here. I need a categorical variable now. There's not too many categorical in this data set. Handedness, that one never works. Let's do, sure, why not? Let's do handedness. So, oh, wait. We could do something really cool. That seems practically significant, but how large of a difference is... That's a really good question, Kitty. How large of a difference is practically significant? Well, such a good question. That is the hardest thing. Let's look at GPA and see right here. Okay, so I'm going to think of something as in 2 pounds in this case wouldn't be. Yeah, exactly. It's all very subjective. That's the hardest thing about practical significance. So if it was 2 pounds between males and females, I'd say, well, they're basically the same weight for the 50th percentile. GPA, if we're talking about the average, I'd maybe say about 0.2. I'm thinking about this beforehand. Like, I'm not going to look at the data yet. I'm going to say if males and females differ by about more than 0.2 and it's not by chance, then I think that's pretty big, because that's almost a quarter of a point, or I could say around a quarter of a point. But in my head, I'm thinking if this difference comes out to more than a quarter of a point, then I'm going to think it's a pretty big difference. And let's see here. What is the difference between males and females in their GPA? And did we get the output? It looks kind of close. Oh, good. We did get a ooh. This data is skewed, I believe. Does everyone see this right here? We can also analyze. Let me do QQ plot on that. Survey 10. And we want to go to GPA. I love the autocomplete. Oh yeah, that's not normal. This would be a great one for the test. Dang it, I used one of my test examples. But that really shows non-normality. So GPA data is not normal. And it was kind of hard to see in this picture. This picture is divided up between males and females, but there is a bit of a bend. I just wanted a bigger version of it with all the data. So GPA is not normal. So once again, and you could see the histograms, but make sure to look at QQ plot. And I do like to make these bigger. When I make them on the test, usually I maximize this window and screenshot and do it that way because that makes the things over there smaller, or makes these little text box smaller. So we're once again going to use the medians because of the skew of the data. Now, when I look over here to see the difference between males and females, it's almost a what of a point. Look at the difference between males and females. Practically speaking, the difference between males and females when we compare medians is basically a blank of a point. And you could find out exactly mathematically, but it's basically a blank of a point. And I thought of my kind of threshold beforehand. It's basically, if you see right here, this difference right here, it's basically a third of a point. So the difference between males and females in their GPA is basically a third of a point. On the test, you could write 0.32, just subtract the two right there to get the difference. And yeah, I think if one group is scoring a third of the point higher on their GPAs, that's pretty big difference. I mean, one, it's not by random chance. And two, we are sure it's not by random chance. Sorry, wrong one. So here's the one of, is it by random chance? Are we confident it's not by random chance? And then right here is the difference practically significant? And if it was normal, if this distribution followed the red line pretty well, then we would use the averages. And just so you can see, I'm wondering if this will work. I'm going to try a trick here. So let's do this. Let's go right here and go data. That's not going to work. Maybe. Oh, I have an idea. Okay. Survey 10, square bracket, and let's do first. Oh, it doesn't like that. Wait, that's rows, columns. Oh, is the first one not? There we go. That one looks kind of not normal. That one's pretty moderately not normal. Very not normal. Right here. You see, we're just changing this number. I wish it would. Ooh, what is that? Whatever the sixth variable is. 1, 2, 3, 4, 5, 6 texts per day is extremely right skewed. If you see, we observe someone texting 1,000 times. That is ridiculously not normal. If you were to make the histogram from it, it would look extremely right skew. That one's also right skew. Oh, that's insane. I think that's, what is that? Bunch of zeros, number of tattoos, and then we're going to get number of piercings, weekly hour video games, all of this right here. We might get something more normal with these higher ones towards the 15s and 16s. That's still a little bit skew. I mean, these you could almost use normal techniques on. They have a lot of high observed values, and these are like the more attractive ones. But I'd probably make it look a little better than this. But this one is not the worst. We did see some really bad ones that would indicate non-normality. Like that's ridiculous. You can't use the normal curve on that. That one's horrible too. So these are, if I do something like that on the test, you're definitely looking at medians. If I did something like this on the test, this would probably lean more towards means. I might want to make it look a little bit nicer since it's a test. I want everyone to kind of agree on the answer. But you could maybe use means on this one. It's got problems on the high side, but it's not horrible. And if you want to see how it looks, you can just change this to hist right here. And which one were we doing? Yeah. And once again, what is it? It's not bins, breaks. That's what it is. They need to call things like bins or something. And you can make it very sharp like that. Or you could go right here and do something like this. And if you notice, the way I do the bins dictates how this will look. So you can't look at a histogram and be like, I understand what's going on. Yeah, it will. The practice tests are posted. I'll be going over those in class. So make sure to look over those and bring questions for class. The last portion of class, we're doing practice test. So next week, we will be looking over the practice test, anything you guys want from previous tests that I have posted, but go to where it's on the midterm week. Have other people seen that? But the practice tests are posted. There's, I think, 3 of them. Don't look at anything with multiple regression. Don't look at anything with multiple regression. We're only going through simple linear, but I have 3 practice tests posted. I designed my tests like Petrie's tests, so make sure to look that over. And I'm probably going to do I am going to do a mosaic plot here now. Let's do a mosaic plot. So definitely take a look at those. Let's see if someone's class level. Let's see if someone's class level is explained by, there we go, survey. Oh, it doesn't like that yet. Survey 11, $ class level is explained by. I want something to actually work out with it. I want something to actually have a good relationship. And we're looking for something categorical here. Churchgoer. Well, does churchgoer explain your class level? Oh, this might actually work because maybe as people become juniors and seniors, they're less likely to go to church. So we'll go right here. And let's go ahead. This is survey 11 data. And we'll get a mosaic plot here. And I'm going to reverse the 2 variables. I wish there was just a quick button to reverse. There's not, though. So definitely look over the practice test posted. And remember, on Monday, Tuesday, we're doing a little bit of an activity, and then we are reviewing. So here we are. It's a little bit out of order, and sorry the graphic's so cluttered. We just don't have that many freshmen. There's sophomores, there's juniors, there's seniors, and there's sophomores. This data actually needs to be ordered. It's all right. Sophomores are the least likely to go to church. Seniors are the most likely. Excuse me, I reversed it. Sophomores are the most likely. Seniors are the least likely. That just didn't make sense to me. If I had to think about it, I'd say seniors are least likely to go to church. And wow, this is a fun test question right now. Look at the results and tell me with the results, is this difference we observe between class levels and whether or not they go to church statistically significant? So you should be able to tell me if this difference is statistically significant. We've got part of the output on the screen right now. Once I say, is the difference statistically significant, you should think about p-value. You should be like, I need to look at that p-value right now. And the p-value is 0.03, so the difference here is statistically significant. The difference is statistically significant, and I really like the confidence interval for it because I could ask, are you confident that the difference is statistically significant? Are you confident that the difference is statistically significant? And the answer would be yes, because 0.05 is not in this interval. 0.05 is not in this 95% confidence interval for what we think the p-value is, so definitely it is, at least in our minds, we're confident it's statistically significant. But here is a decent question that could be on the test, because we should understand where these p-values are coming from. If I were to run another permutation of this, will I always get statistically significant results? And the answer, or will I always get a confidence interval that does not contain 0.05? And the answer is no, my confidence interval might contain 0.05. If you notice, a lot of people have said this just says estimated p-value, and that's because it's a simulation right here. We are simulating this p-value, and that's why these results on the far right changes. The results over here change because we are constantly simulating a new p-value, and that's why you see this histogram change. Let's review what this graphic is on the right, which we've seen this graphic already a few times now. This graphic here on the right shows us our results with the red line. Anytime we see a permutation graphic that we've created, it shows us our results right here, and then we see the results created by random chance via random permutations. So all these results here are by random permutations, including the ones over here. I was circling these because these are less than our result, and right here these are greater than our result. And so the p-value would be that there is 4%. This percent right here is the percentage to the right of this red line. To the right of that red line is 4%, which tells us in our simulation, 4% of the time, we got a discrepancy as large or larger than our discrepancy. And that's a great interpretation right there because the p-value, I'm going to say this one quickly, is the probability of our results or results from our stream happening by random chance variation given that the null is true. Well, what it means in this context, and don't worry, that's just the general p-value interpretation, is that the probability of our results, this red line, which was a discrepancy of this, or results more extreme, occurring by random chance, which is the permutation, would only happen about 4% of the time. A result as extreme or more extreme than our result by random chance would only occur about 4% of the time. The permutation procedure is very important to this test, understanding theoretically what is going on. What does it mean for something to be a random permutation? We haven't talked about this in a while. We're still using it. We can still use it on our regression, because we can go here and do a possible regression. And let's take that first model we made, and we see here the same sort of result. And it gives us the p-value. So what is a random permutation? A random permutation is you take all the data points and just mix them up. You just mix them up at random. Permutation means just kind of a different assortment of it, like you can permutate things and just mix them up. So we mix things up and we see what would happen at random. And I really like this one for the whole talk on it, because when you look at this line right here, this is our observed line. And then these right here, these boundaries are what we would expect by random chance. And so is our line within the bounds of what we would expect by random chance? Yeah, our line looks like what we would expect by random chance. And then over here, we see the reductions in sums of squared error, because this is now a regression, that we would get via random chance. And the reductions we get via random chance are generally very small, and our reduction, the red line, is pretty small. And the shading to the right, now there's a lot that are very, very small. Remember, this is a bin, so it doesn't necessarily show you everything perfectly, because apparently 72% are as extreme or more extreme than our reduction. As in, all these models over here, these ones that did like this, did better than our model. And all of these models are by random chance. So it seems like our model is just one of those random chance models that just doesn't really explain anything. And if it does, it's just by random chance. There's probably not a real relationship going on here. We can look at one where we actually do explain, and I think Model 2, we actually had a much better version. So in Model 2, we did a better job, and boom, look at that. Now you can't even see the reduction in sums of squares error from the models that are by random chance. And that's why the estimated p-value is 0, because there's no model that does even as close to as well as our model does. So the permutation procedure says, take all of these points right here and just shake them up. Just shake up the points. And then just figure out the linear relationship between them. And when you mix up the points and then create the line, is it as strong or stronger than yours? And the answer is nothing turned out the way our data did. So the relationship in our data does not look to be by random chance. How do we know if it's by random chance? Well, we just create random chance data sets. And this is really one of the best ways to make your p-values right here, because it's just simulating them. It's just saying, well, what would happen by random chance if we had no relationship in the data? And that's how we do the classical null, is that there is no xy relationship, that the slope is 0. And if you notice, the naive model goes right through here. The naive model being the mean of y goes right through there. So I could actually look at this data set and tell you that the average person is probably about 68 inches tall. Ooh, that'd be too mean of a test question. Too mean of a test question would be like, tell me how you know the average person is 68 inches tall or stuff like that. But if we go here to that data set and we run the model, we just go to mean and we go to survey 10 and we go to height. I'm going to say it's about 68.1 and it's 67.7. So very close to 68 inches. It's just very hard for me to tell over here on this scale where that's hitting right there. So apparently that's 67.7 where that hits, because that's where the flat line would go through. That's the naive model, and the naive model is the mean of y. So what more questions do you have? We've talked about the permutation procedure a bit here. We've talked about confidence intervals some. What do you guys want to talk about? There won't be any... There can be questions on the theory of coding a little bit. Things like why we set seeds. That's up for game. I won't have any big, you won't have to write code on the test, so you won't have to do that. There might be more theory related, like when would we use a for loop? We did that earlier on in the semester, but you're not going to have to write a for loop on the test. I want you to understand theoretically what is going on. But there's, just theory questions can be on the test. Like, why would we use a for loop? And the answer for a for loop is very simple. See, I'm taking my questions now. It's even better if I do it in the review than if I put it on the test. It's like, oh, we should know that. One of my favorite things to do, and I swear I need to do this for my nephew, is to make a for loop that just prints the 9 times table. I figured this out one day and I was like, that's so cool. So we put this right here. You will not have to write a for loop for the test. I just want to repeat that repeatedly. You will not have to write a for loop for the test. And let's do this and put a comma. And do I know how to do my backslash today? That's always the question. So nope, I never get that backslash right. Never get that backslash right. Or what does it? Oh, maybe I did. Maybe I did. I meant to do times 9 right here and then comma. Okay, now it should work. There we go. Hey, got the for loop. Got it right there. Not first try. Just forgot my I times 9. I was thinking about the backslash n as I was typing it because I can never. I'm pretty sure that's backslash, but I don't know. I don't know how to recognize a backslash or forward slash. Can we go over typical most missed questions? Yeah, we'll do that next here. And so typical most missed questions, I like that. If you notice here, a for loop just lets you do a task multiple times. You can do a simple task. Like I can just make this vector right here and it'll give me that. Then we could also throw it inside of a function and make it even easier. So let's remove it here. It's not as easy when my keyboard is up here. Let's go ahead and remove this and put it in a function and call it function math table. And let's just put it inside of here and just do one last thing, then we'll go over most missed questions. So yes. Cool. I think this will run now. Does it work when I do that? It does. Unexpected. Well, darn it. What's it mad about? 2 seconds. It says unexpected. I think it might have been inside of code. Well, I'll have to debug this later. For loop. For loop runs. Oh. This is what happens when I code too quickly. Okay. N should be right here. There we go. And little fun thing right here. You can just do math table. If we run math table, it'll give us the table right here. And if I write 5, it'll give us the table to 5, or it should. End equals 5. Let's try that. And then let's look over most missed questions. Oh, it's not working. Oh, haha. There we go. Too quick of clicking today. There we go. And now it'll do 10 by default. So if I just run that, 10 by default, or I can enter 99, it'll do that. There we go. So pretty nice and easy to make a function and see what's going on. Functions just let us build our own world and have controls over what's going on. I could even change the number it uses and all that good stuff inside of here and make any table I wanted. But functions, if you start getting the ability to build functions, this is my whole selling on this, and can write your own functions, have them do what you want. You're just writing your own programs then. I mean, that's how you make your own programs. It's all built on functions. So the typical most missed questions, especially the permutations, people just really don't have a good grasp of what's going on right here. Like when we run the associate function, this will do a permutation procedure also. So you see the permutations here, and then on this one you see the permutations down below. Hence why it's taking a moment to load them. It's doing permutations. So the visualization of the p-value is actually all the way over here. We didn't even mention correlation, so let's go ahead and grab one of these where we can do correlation, and we can make, I think people just don't realize what a permutation is. I think because it's a new topic. It's like they've never heard it before, and they're like, I have no idea what these permutations are or why we use them. So you notice here we're going to get permutations down here. Now when we look at this result, we have a result as extreme or more extreme than ours would be in terms of absolute value. Oh, we didn't even talk about Spearman and Pearson. But permutations, knowing that these results right here are the results we would get from random chance if we just mixed up x and y, which that's what a permutation is, and then we saw what the correlation was. So the correlations we generally get by random chance are close to 0. I mean, if you have two things that are just randomly together, then the correlation for those two should be very close to 0. But what we see also is that our result, or result as extreme / more extreme, because you see it does kind of the absolute value of it. It looks at as extreme because 0.6 is as extreme as negative 0.6. With that in mind right here, we can see our result is basically impossible by random chance. Basically impossible. Anything can occur by random chance. But the p-value here would be 0, or estimated to be 0. And if we scroll up just a little bit in the output, we will see that both of these have an estimated p-value of 0. Basically, a lot of people don't understand what's going on with the graphic. So yes, and I like this. Spearman would be used for more skewed data, yes. Basically, the key characteristics of Spearman are that it handles monotonic data. Let's look. Is our data monotonic? Monotonic means it goes in one direction. And yeah, that kind of does go in one direction. It pretty much just kind of bends. It's got a little bit of bend, but it goes in one direction. Spearman also handles outliers. Does our data have outliers? Our data does have outliers. Do you see the outlier there, kind of there? But these are your main groups of outliers here, and this one over here. You just got some low ones and some other ones. So it handles monotonic, handles outliers, and it handles heteroscedasticity. We do have a little bit, I mean, this is more outlier issue. I don't know if this is a prime example of heteroscedasticity, which is unequal spread, but no, that's all right. Your questions are great, Kitty. They're great questions, and I'm going to try to answer them fully. No, you're giving great questions. So we see, and I'm glad. I like when the chat is talking. It lets me talk more on things and lets me know what you guys want to know. So the more people in here, the more I can direct towards what questions you guys ask, and I appreciate your questions. So right here, we would definitely use Spearman, and it's really apparent. One of the questions asked on the homework, did the significance matter if you chose Spearman or Pearson? In this example, there's a statistically significant relationship with Pearson. There's a statistically significant relationship with Spearman also, and we are confident of this because the intervals for the p-values do not contain 0. I mean, it's 0.05. Sorry. My gosh, we've been doing the other chapter so much, I'm automatically thinking about it too. Because we do not want the intervals for the p-values to contain 0.05. I was saying that earlier. It's easy to get mixed up though. Remember, this is saying what we think the p-value is, and yeah, we think the p-value is basically 0, and we're pretty confident of that. So this is a statistically significant relationship that is best modeled by a Spearman rank correlation. The Spearman rank correlation is the best way to look at this right here. And you see it in the difference. We're not going to choose it because Spearman is higher, but generally speaking, if one is better, it will be higher. But Spearman also works for Pearson because Pearson is linear. Pearson is just linear. So when you think about Pearson correlation, it's linear. And there is some linear aspect to this. We saw it earlier. We can go back to that graphic we made earlier. There is a linear relationship to that data. Where do we put our line in? I thought we did the line. Oh, have I saved over M2? Maybe I have. But it doesn't it says using, I think I saved over my data or something. It's only using the first 2 5 regression coefficients. Oh, let's go right here. Well, it's not like that. Height, weight, model M2. Let me try this. Let me remove this right here. I never thought that would have a problem. And then let's run this. And, well, that's weird. Didn't know it would have a problem doing that. You learn something new every day. I'm going to do one more thing. What is it? Line width? I can remember line width. Line width is something in here. We will not worry about it. But you can make that line a little bit thicker and it looks a little bit nicer. But this relationship right here is has some linear aspect, but it's better described by a monotonic relationship. And we can see that with something we really haven't used much, but you can see the relationship to it that has a little bit of a bend. Really, you're not getting much out by bending it another way, but if you look at this bend from the red and the green line, we can see some nonlinear aspect to it. So you can compare just your linear model right here, or let's do this. You can compare the nonlinear aspect to it. So there's definitely something nonlinear going on right here. So I would definitely, if you look at the red and the green, these are kind of overfit. More on that later in the class. I would definitely go with a Spearman for this relationship. And so, knowing the key characteristics of Spearman, I could say, name 3 key characteristics of Spearman. That'd be a fair test question. Or name 3 things Spearman deals best with. Spearman deals best with heteroscedasticity, outliers, and monotonic relationships that are nonlinear. So it uses monotonic data. It has to be monotonic. You can't have it go in two directions. You can't have it be parabolic. And I know you see lines in here that do kind of wiggle about, kind of crazy, but if you notice our data kind of levels off. It does go down a tiny bit at the end right there, but it does kind of level off. Like, yes, doing some sort of leveling off right here seems to be a good idea, and that probably explains it pretty well. Like, it's a decent way to explain the relationship. Once again, all models are wrong, and this model has a bunch of outliers, and we could even try to remove that person there. So, yes. I'm trying to think of other generally missed questions. I think the big generally missed ones are the theory ones. Like, why would we use Pearson instead of Spearman or Spearman instead of Pearson? Pearson's really the default. Pearson is, it's a linear relationship. Most people understand a line. You have to explain to someone what Spearman is, that you're using the rank of the relationships, and that makes it a little bit more confusing, and confusing is not good when you're trying to make decisions with data. Let's look at, I'm trying to think what other output we've created that we haven't looked at. We could look at the predict function right here, and let me make a data frame right here. And I'm not making a data frame right there. Let's make a toPredict data frame. And I'll mention this for those doing the take home. When you make a data frame, if you have to enter in multiple things, well, one, you don't have to use the concatenate if it's just one value. So a little bit of tips here. You put in your x's, whatever you want them to be. And if you only have one value of the x, you can just enter in one value. But if you do have multiple values, you have to use the concatenate with the values between them. And of course, there should be an equal number for what you have. If you have, oops, concatenate goes out there. And so this is, Q1 has this many values, Q2 has that many values, but a little bit of help for the take-home, because I think like Will's doing the take-home, and I really appreciate Will coming in and saying, hey. So let's go ahead and let's make our data frame right here. Let's go, we need weight. If you notice, weight is on the x-axis, and then, sure, it'll run the same way. 190. So that makes the data frame right there. If you notice, it's toPredict data frame. It just has one weight inside of there. Just once again to reiterate, if I am just storing one value inside of here, I don't need to concatenate, because concatenate is used when you have to store multiple things into like a vector, and we don't need to do that technically right there. We only do it if we have more than one value or are required to. So now I'm going to use predict, and I think it was model 2. So I'm predicting using model 2, and model 2 is this line you see on the screen. This line previously. Let me go back and bring it back up here. That is model 2, that red line. And when I do model 2 right here, I can put in new data equals, and let's put in my data right there, and then interval equals, and we want to do prediction. There we go. And so right here we see some values. We see the predicted height of Brian. So I weigh 190 pounds, and we predict that Brian, I'm 95% confident, that the prediction of, or the height of somebody who is 190 pounds is contained in the interval 63.2 to 77.2. That's pretty large. It's pretty large. We can actually see this visually over here. And let's look at this visualize right over here, where we have 190 pounds about, and you notice this goes to about 63 right here. So if I were to trace over, that's why we're hitting there about 63. And if I were to trace over right here, that hits at about 77 or so. So just when you trace over right there with these lines. And so understanding what the predict function does, and actually how to make predictions. Now, if I wanted to do this prediction by hand, so this is a decent test question once again, if I want to do these predictions by hand, I need to actually make my model. I need to go right here and grab the numbers. Copy paste doesn't work, gotta remember that. And so we could say predicted height, and then we save into it the intercept. And so we're basically writing the model out right now. Plus, and then we put in here the slope value, and then we times that by weight. And we can do one better. We can just go here and say weight, and actually, will this do it? I think there's a way. Oh, I think I'm going to try something that I learned a long time ago and I've forgotten. I hope that works. If it does what I want it to do, I'll be very happy. Nope. Is it you put it on the outside? There's a way, and if someone says in the chat, I'll give you mega points. There's a way to make it. No. There's a way to make it return the value after you run it. I know another way, so I'll use that way. So I want it just to return the value. I want to run it as one line, and right there. That'll do it too. Ooh, error to apply non-function. Was it not like weight is 1.9? Oh my gosh. Is anyone saying that in the chat? That's low-level error. That's a low-level error right there. I can't believe I did that. We all make mistakes in coding. It happens. There's no perfect coder out there. So I was thinking about this, and then I forgot to put the star next to it. I've told many people that, yep, that does it. I remember that works. So if you notice, putting it inside of that parentheses right there actually returns the value from what I create. So that also will create the value of the predicted height, and it also returns the value once I run it. So a little bit of a neat trick right there if you want to see what you've created. I remembered it being like that. You just learn so many things over the course of learning code, and then you forget how to put a star between two values. So you forget like one of the first things you learn in R. And then they make you do different things in MATLAB. But if you notice right here, if I change this to 180, I want to point something out. I can tell you what the fit of the line is. The fit of the line is going to be 69.53. So the fit of the line is 69.53 because the fit of the line is the actual prediction of the line. So when I run the equation and I put in the intercept and the slope and I multiply the slope by the weight, I get where this line hits at 180. That's what this output is showing me right here. This output, when it says the fit, is giving me the line where the line hits mathematically by solving the equation, and then the lower and the upper are the interval for an individual. Individuals have prediction intervals, and the mean would be confidence intervals, and we're more confident about the mean, but once again, the line is still our best guess. So theory like this right here, this sort of theory is that when we make our predictions, if it's for the mean of the line or for an individual, both are the same. We would still predict the mean of the line going through where the line goes through. I mean, that's our best guess. We'd still predict an individual to have a value where the line is. But the intervals, whether it be prediction or confidence, vary because there's more uncertainty in an individual. Let's see if there's any last questions. We hit upon a lot of theory with this review. It's hard to cram all the whole semester we've done so far into 90 minutes. But let's see if there's any questions about anything. Remember, in class, we are going to go over practice test questions. We'll do about half class, half review. So another good 45 minutes of review. And then the test is at the end of last week. I hope this has been very helpful. I always look over the file that I have, and I'll be posting this file after this. I'll log off, and then I'll put this on the midterm. I'll put like, you'll just see it appear. And then I like to look at this and think about, okay, what did I do during the review? And how can I augment the test questions? So definitely focus in on what I did here. Any output I made throughout this whole review, even if I didn't go all through the output, there was a lot of output created. Just kind of knowing what everything means. Here's the mosaic plot, and you can see the expected counts. So knowing how we use mosaic plots are categorical. We can actually see the observed amounts. These are the observed. These are the expected. We can get the cell chi-squareds, add them all up to get the test chi-squared, and that's actually our discrepancy here. The discrepancy is the test chi-squared, which is the sum of all the cell chi-squared discrepancies. And here we can see what percentages of people go to church and don't go to church. This is from a much earlier assignment. These would be they're either the row or the column. I guess it's the marginal. Let me think right here. This is freshmen, and so this is a conditional display. This is a conditional display because given someone is a freshman, what's the probability they go to church? And given someone is a junior, what's the probability they go to church? Conditional displays are when you can say, given this, what is the probability of this? So it looks at, hit a button there. It looks at the probability of each of the insides, each of the inner parts. And if we wanted to do the marginal displays, those are not calculated. But to do the marginal displays, they are right here. Here's the marginal display of going to church. The marginal display is the display in the margin. So that's the marginal display of going to church. And then this is the marginal display of people's class level. So two different things right there. And just a little bit more of the mosaic plot output and understanding what's going on. These are just how many people in each group. And then these are the totals for each variable. Then the expected counts, which is row total times column total over grand total. And then the conditional displays, it actually says conditional distribution right there. And that means given someone's a freshman, and apparently I'm looking something up. And then the estimated p-value, which is just that tells us that our results were not likely by random chance, but we are uncertain if our result is statistically significant. Definitely try to go through and read the output, especially when you get to regression output. Remember, we focused a lot on regression. So with focusing a lot on regression, make sure you can read all the regression output. Yes, so many of that mosaic plot. And here's some regression output. Right here we have the estimate of each of the coefficients in the model. This is a multiple regression, which won't be on the test, but it still has estimates of coefficients. Then we have our uncertainties. We didn't talk much about standard errors. Remember, not every standard error is the same. That's, I think Kitty was asking, what are common things people miss? Not every standard error is the same. So you can't always say this is the typical miss the model makes. No, this is our uncertainty in the estimate of the intercept. So the intercept might be off by about this much. It's not that it is off by this much. It's like, well, the intercept we think is 52.67. But, it might be off by about 0.79. We don't want our uncertainty to be large. We want our uncertainty to be relatively small because that'll make a high t-statistic, which will make a low p-value. The t-statistic is just the estimate divided by the standard error. It's very fair game for me to blank out a value in the output, like a t-statistic or both t-statistics, so you can't backward it. Sorry, that's mean. But I can blank out a t-statistic or more and be like, solve for the t-statistic. It's just the estimate divided by the standard error is the t-statistic. So it's not a big math formula. It's just the ratio of the two. And so you can see here, this one's a little smaller than 1. It's 0.82. And you really focus on the absolute value of the t-statistic. It'll be positive if the coefficient is positive, or the estimate of the coefficient. It'll be negative if the coefficient of the estimate is negative. And then the larger the t-statistic, the smaller the p-value. So these are scientific notation for these p-values, denoting that they're very small. One last thing, sometimes I throw something about the residuals, and we want the residuals to look normal. If you notice here, there's a very large minimum residual. Let's do it for our model 2, all the way back down here, and kind of end with that, because I think that's majority of the output covered now. So with this simple linear model, which is what the test is focusing on, I'm going to interpret all this output and go through it real quick here. It seems like there is an extremely large negative residual, and actually we can see them. Hello, that looks to be them. That looks to be about 22 below. So, or 21 rather. So there seems to be a very large residual that is negative, telling me that the model massively overpredicts someone. So maybe there's a problem with the residuals. We'll have to examine further with the residual plot. Looking at the estimates, the average person who weighs 0 pounds, which is illogical, is expected to be around 56.34 on average. And that's illogical because you can't weigh 0 pounds. And if you did weigh 0 pounds, you wouldn't be 56.34 inches tall. Interpretation of the intercept. Oh, interpretation of the slope. Ooh. If you have watched the end of this video, please know how to interpret the slope. Here it is. I'm going to try to do it in the general form right here first. 2 observations, whatever they might be, that differ by 1 unit in x are expected to differ by blank units of y, where the observation with the higher x is expected to have the blanker y. And you'll hear me fill this in a moment, because if it's positive, then you expect higher. If it's negative, you expect lower. So 2 people, if you notice that's my observations here, 2 people who differ in their weight by 1 pound are expected to differ in their height by 0.073 inches, where the individual who weighs more is expected to be taller. So 2 individuals who differ in their weight by 1 pound are expected to differ in their height by 0.07 inches, where the person who weighs more is expected to be taller. The standard errors here are a relative amount of uncertainty. If you notice, we have here basically a 20 ratio. If you say 7 and 0.35, or that'd be right, just kind of moving the decimals around. But it's a 20 ratio. That this number here, the estimate is 20 times larger than the standard error, and that is a very, very large, and means both of these are very significant. The intercept's more significant, but we don't care that the intercept's not 0. We care that the slope is not 0, because that is the significance of the line. Would the typical miss sort of be the sum of the typical miss of the intercept plus the... I think I'm confused on your question. Would the typical miss sort of be the sum of the typical miss of the intercept? Well, remember, we don't usually interpret this as the typical miss of the intercept. It's kind of our uncertainty in the intercept. It's not saying we typically miss the intercept by this much. I think since we learn residual standard error first, we usually think typical miss. So the only time, so there's a great note to take right here, Katie, is whenever you say typical miss, you're talking about residual standard error. So when you say typical miss, make sure you're thinking about the residual standard error. But when you think about uncertainty, so you could say that's our uncertainty in the residuals, which we see right here. But this is uncertainty in the intercept, and this is uncertainty in the slope. And I hope that makes a little more sense with that. So those are uncertainties in those quantities we've estimated. These are two different quantities which we have estimated, and this is our uncertainty in each quantity related to it. We don't want uncertainty in each quantity. The intercept we wouldn't really mind. It's just, I don't know. But we really care about the slope because that's the xy relationship. Since estimated y b0 plus b1x, so estimated y would be typically off by how much b0 to? I think, did that help out? The typical miss the model makes when predicting somebody's height is about 3.554 inches. So when you interpret the residual standard error, that's where you would say the typical miss the model makes when predicting height is about 3.554 inches. This standard error right here is the uncertainty we have in the estimate of the intercept, which is 56.34, is about 0.589. That's just our uncertainty in the estimate of the intercept. Where weight, we would say, our uncertainty in our estimate of the value, the coefficient of weight, let me repeat that. Our uncertainty for the estimate of the coefficient of weight in this model is about 0.0036. And in the book it does say it's about how much we might be off from the truth. It's about how far we think we are away from the truth. But that doesn't mean we think we are this far away. It's just saying, someone says, I'm going to show up at 5, but maybe within about 10 minutes of 5. So they're not saying they're going to be 10 minutes away from 5. They're saying that's kind of their boundary. And this kind of gives us the plus or minus on it. Don't literally use it as a plus or minus, but it's that idea. Now you can use it as a plus or minus to create the confidence intervals. And that's why it's about how much we might be off, because we use it to create the confidence intervals. And if you see if I run confident on this model, it'll simply use those numbers right there to create a confidence interval. I think this is model 2 right now. It'll use those numbers to create a 95% confidence interval, and it's literally just going up or down 2 standard errors. So if you look at right here, it just adds and subtracts 2 standard errors to that. Awesome, Kitty, I'm glad to hear that. So those are our uncertainties in the coefficients of our model, where this is our uncertainty in the residuals, and that's our typical miss, because a residual is how much we miss by, and then we're saying, well, we think we usually miss by about this much. It's how much we think we will miss by, what the residual usually is. And it's not saying we will miss by 3.55. It's just saying, on average, we kind of miss by about this much. I think that's got it. I think we just did all the output. R squared is just 36.13% of the variation in height is explained by the variation in weight. So R squared percent of the variation in y is explained by the variation in x. Our model is statistically significant right here on the p-value. Once again, do not mention degrees of freedom. They're used for calculations. They're good, but we don't use them in this class because the business world doesn't start talking about degrees of freedom. So, and the F statistic, last thing to calculate right here, tells us, we could interpret it a few ways, that the reduction in sums of squares error that we observed going from the naive to the model we have, we don't have a full model, we just have a one variable model. The reduction in sums of squares error that we observed was 394.2 times more than what would we expect by random chance. So this is how many more times what we observed was more than we expected. And I think that's got it. We went 90 minutes or so. If anyone else has any other questions in the chat, I can't see how many people are viewing. But is everyone good? We went through regression a lot, went through a lot of output. And yeah, we have it. Quick question. Go ahead, ask away. And I pause afterwards because there is a delay, so I have to make sure to pause. I don't just say, we have it, bye. Ooh, I'm looking up. My screen is up if you see me looking up. Screen's on the ceiling. We'll see if Will or anyone else. Thank you so much, everyone who came in. I really appreciate it. If you guys got more than 1,000 points for being here, if you talked in chat, you got that 1,000 points at least. I really appreciate you guys being here. The questions definitely make it. Between two models where the greater uncertainty in the slope in one model, that model overall would have a greater uncertainty, right? So you're saying the model, well, so remember the uncertainty in the slope would be relative to the value of the slope. So a model could have, this is a good true false question, but I hate true falses because you can guess and have a 50-50 shot. So what you really care about is the relative uncertainty. So right here, the relative uncertainty is what matters because this uncertainty is tiny. I mean, if you think about that in terms of dollars, that's like not even a penny. So it's very, very tiny uncertainty, but it's very, very, the slope is also small. Oh, they have the same slope. Yes, so where two models greater in slope in one model. Yeah, that's literally what it is. Also, the standard error right here, they all kind of go together, or at least the standard error of the slope and the residual standard error is going to go kind of hand in hand. At least, let me interpret that again. The residual standard error is actually going to help us with our standard error of the slope. So the residual standard error is going to tell us information in the standard error of the slope. So if a model has more uncertainty in the slope and they both have the same slope estimate, logically speaking, it would have to have more uncertainty in the residuals. So the uncertainty in the residuals is used to calculate the uncertainty of the slope. If you remember, we have that formula with the root mean square error times the square root of x minus x bar squared, the distances you are away with n minus 1 on the bottom. I won't make you use that formula. We might talk about theoretical. We might talk about that in class. But if they had the same estimate of the slope and were basically the same model, and one had more uncertainty in the slope right here, well, then also it would have more uncertainty in the residuals. And these are not the same quantities, but the standard error of the slope is calculated from the residual standard error. Not purely. There are other things that go into the standard error of the slope. And technically, this could be a huge trick question due to sample sizes and all these things, but it might not be a good true false till I think about it completely, but a steeper slope would be more. So a steeper slope would need a very large uncertainty. The steeper the slope, then the more uncertainty you would need to make it less significant. It would just be the ratio. Like if you had a slope of 10, it would not be significant if your uncertainty was 8, because your t-statistic would be 1.25. If you had a slope of 10 and your uncertainty was 2, your t-statistic would be what? If you had a slope of 10 and your standard error of the slope was 2, your t-statistic would be 5, because it's the ratio of the slope to the uncertainty in the slope is the t-statistic. And then also your 95% confidence for the slope with a slope of 10 and a standard error of 2 would be basically 6 to 14. So just because you go plus or minus 2 standard errors. So if you have a, whoops, just hit my hand on the desk. If you have, probably everyone heard that. So if you have a, bounce the camera. So if you have a very high slope, it would take a very large amount of uncertainty. It's all relative. So you can't say the slope is high, the model's good. You have to say the p-value is low, telling us that our slope is statistically significant. Does that help out? Does that explain everything? I think we're good. See if there's any other questions. It's like a 7-second delay. There's quite the delay. I thought YouTube, I put it on ultra low latency, and so I thought it had like a very, very short delay, but it is a little bit long. I'll go for another 30 seconds or so, and feel free to ask the questions if you have it. Remember, we will be reviewing in chat in class too, but I really appreciate you guys coming in. So we'll see. Looks like we're good. So I'll be logging off here in a second. Well, bye everyone. So as I say bye right here, now I start logging off, and we wait just a half second here.